Good evening to all. Today we are going to discuss again very important thermodynamic process, that is polytropic process for real gas application. I'm sure this video is going to be very interesting, so please do keep watching until the end and subscribe my channel, and don't forget to hit the bell icon. Thank you. So let's begin the discussion on thermodynamic process for polytropic process for real gas application. Before that, let's understand the thermodynamic system. So if you see thermodynamic system, it is related to gas, and gas can be air, gas can be any hydrocarbon. So when heat is given to the gas, that means heat is given to thermodynamic system, it is positive. When heat is removed from the system, it is negative. When work done by the gas is positive, when work is done on the gas is negative. Gas is thermodynamic system. When heat energy of the gas increases, that means heat energy of the system increases, it is positive. When decreases, it is negative. This is as per sign convention, as per first law of thermodynamics. Types of thermodynamic system: open system, closed system, isolated system. In case of open system, mass transfer occurs, you can see here, and energy transfer both. In case of closed system, mass transfer doesn't occur, but there is only energy transfer. In isolated system, neither mass transfer occurs nor the energy transfer occurs. Real gas equation of state, PV is equal to Z N R U T. On simplification, we can write PV is equal to Z R T, and this is very vital equation for real gas application, where Z is a compressibility factor. Now work transfer on PV diagram for closed system, work transfer on PV diagram on open system. In case of closed system, area under the curve on x-axis is equal to work transfer. In case of open system, area under the curve on y-axis is equal to work transfer for the open system, and by formula work transfer for a closed system is integration PdV, and for open system minus V integration of VdP. And as per sign convention, work done by the system is positive and work done on the system is negative. This is true for closed and open system both. And this is again as per sign convention, and work transfer per unit mass is called the work head or the head. Energy transfer for the closed system is equal to internal energy change, and which is expressed as integration of CV dt. So we can write energy transfer for the closed system is equal to integration of CV dt. Energy transfer for the open system is equal to enthalpy change, and enthalpy change written as integration of Cp dt. So energy transfer for the open system is equal to integration of Cp dt. Now, as per sign convention, energy of the system, if increases, it is positive. When it decreases, it is negative. This is as per sign convention. Now, as per first law of thermodynamics, heat transfer is equal to work transfer plus energy transfer. So Q is equal to W plus E. But the most important assumption for the first law of thermodynamics is that efficiency of thermodynamic machine is 100%. That means the process is very ideal. There is no losses during the transfer of work, transfer of energy, and or heat. With that assumption, as per first law of thermodynamics, heat transfer is equal to work transfer plus energy transfer. Polytropic process shown on the PV diagram and TS diagram. You can see in polytropic process, when compression occurs, pressure and temperature both increase. You can see here when expansion occurs, pressure and temperature both decrease. You can see in this process, compression process, this is expansion process. During the this process, that is polytropic process, you can see there is a little bit heat transfer occurs, and so entropy also increases in compression, entropy decreases in expansion. Now let's derive the polytropic work for closed system. PB to the power n is called to n is a polytropic index is constant. This is equation for polytropic process. And PV diagram, you can see area under the curve on x-axis is equal to work transfer. So again you can write PV is equal to Z RT, P1 V1 equal to Z1 RT1, P2 V2 Z2 R2, and K is Cp by C1, N is a polytropic index, and work transfer for the closed system integration PdV. So after putting all this value, simplify, you can get W is equal to Z1 R upon n minus 1 bracket close T1 into 1 minus P2 by P1 to the power n minus 1 upon n. So this is a expression for work transfer per unit mass. If you want to calculate total work, just multiply this with the mass m. You can see also on this PV diagram, area under the curve on x-axis equal to work transfer. Now the energy transfer for the closed system, it is CVDT. So we can write energy transfer per unit mass is CV into T2 minus, sorry, CV into T2 minus T1. So total energy transfer is equal to mass into CV, that is mCV T2 minus T1. Now heat transfer, as per first law of thermodynamics, you can say Q is equal to W plus E. So you have to add these plus these. So this is heat transfer per unit mass. If you want to calculate total heat transfer, just multiply mass m into this total expression. And you can see on the TS diagram, there is a, this area, this shows the heat transfer. Please note that this is a one condition, that polytropic index n should be greater than k, that is a specific heat capacity ratio, that is Cp by Cv, n should be greater than k. With that condition, when heat is added, entropy increases and heat transfer occurs, and this is shown here. Now polytropic process in the open system, we can again a PV diagram, you can see area under the curve on y-axis will be equal to work transfer, and the same equation, just W is equal to minus integration of VdP. With putting all this value, we can finally come to W is equal to Z1 R N1 upon N minus 1 into T1 into brackets 1 minus P2 by P2 to the power N minus 1 upon N. So this is the work transfer per unit mass. If you want to calculate total work transfer, just multiply mass M with this expression. This will become equal to total work transfer. Now for the open system polytropic process, total energy change, energy change per unit mass is a Cp T2 minus T1. So total energy change mass M Cp T2 minus T1. As for first law of thermodynamics, Q is equal to W plus E. So you have to add Q work plus energy. So this expression is heat transfer per unit mass, and total, if you want to calculate total heat transfer, just multiply mass M with this expression. You can see on the TS diagram also, again condition n should be greater than k. You can see the area under the curve on x-axis is equal to heat transfer. There is a little bit heat transfer occurs here, and so there is also change of entropy. Now let's understand, sorry, this should be polytropic process, not that entropic process. There is a, you can correct it. Example for polytropic process for closed and open system. Nitrogen gas has initial pressure and temperature are 0.5 bar gauge 30 degrees respectively. Gas is compressed such that the final pressure reaches 2.6 bar gauge. With consideration of polytropic process and real gas application, calculate work, energy transfer, heat transfer during this process for consideration closed and open system. Also calculate the inlet and outlet specific volume. Following data are given: mole weight of nitrogen, universal gas constant, Cp, Cv are given, 20.881, 29.187. Compressibility factor at inlet outlet is the same, that is 0.999. Polytropic index 1.5. Local barometric pressure 1 bar absolute. Now these are the given for polytropic process. Convert inlet pressure absolute, outlet pressure absolute, mole weight Z1, Z2, Cp, Cv, Ru, N are given. Now, calculates gas constant Ru by M. Also convert Cp Cv in the joule per kg, dividing M and multiplying 1000, and then calculates K Cp by Cv. Then V1, that is inlet specific volume, V1, V2 is calculated. Then T2 is calculated, and work transfer is calculated, which is coming as minus 3911. Energy transfer is a 49, that is 4916. So heat transfer, if you add these two, it is coming 1005 plus. This is for closed system. In case of polytropic process in open system, the work transfer is minus 5867, and energy transfer is just 6872. So heat transfer is again 1005 plus. So I hope you have enjoyed this session for polytropic process used for the real gas application. Thank you. Thank you for watching.